and welcome to this video on reaction rates. This video is for OCR. My name is Chris Harris and I'm from AlleryTutors.com, and basically this video is a revision video, so it'll basically just give you a whole overview of reaction rates for OCR. Now the slides that I'm using here, they can be purchased. If you just click on the link below in the description box, you'll be able to get them there. It'd be great for things like revision on the move. If you've got a tablet, if you've got a phone, and like that, you can use them on there as well. And you can basically scroll through them at your own pace and use them for notes, etc. So, like I say, this is specifically for OCR, and you can see the specification points there. So it matches the syllabus, so if you're doing OCR, that would be great. Okay, let's make a start. So let's have a look at rate and collision theory. So for reaction to occur, particles must collide. Now, obviously that seems quite obvious, but for a rate of reaction, because we're going to look at the rate bit first, then look at the collision. So for rate of reaction, basically this is the change in concentration or amount of a reactant or product per unit time. So it's always per a fixed amount of time. That could be per second, per minute, per hour, whatever it is, per day. Doesn't really matter. But obviously in chemistry, we're mainly looking at really per second. Okay, so we measure rate by using this formula here. So it's the amount of reactant used or product made divided by time. Okay, so you can measure either of them, and that would tell you the rate of the reaction. So when particles move, obviously they're moving all the time, unless they're at absolute zero, which it never will be, but they move all the time. But most collisions don't actually lead to a reaction, okay? So they'll collide into each other, but they'll bounce off each other, so they won't actually react. So for a reaction to occur, the particles must collide in the right direction, so they must hit each other in the right places, effectively. And they also must have the minimum amount of kinetic energy. If they're moving too slowly, they won't react, okay? So they've got to have the right amount of energy for them to react. And we call this collision theory. So it's the theory of collisions. So let's have a look at another part, which we call activation energy. Now, this is the minimum amount of energy required for a reaction to occur, okay? So we know that obviously for a reaction to happen, we've got to have the right orientation and we've got to have the right amount of energy. Okay, and once we've got that combination right, then we get enough energy for the reaction to happen. So that minimum amount is called the activation energy. And we can use what we call an energy profile diagram, and this can be used to show changes in a reaction. And you can see here that we've got reactants here and products here, and we've got this profile that moves across like this. Okay, so this is the energy changes in a reaction. Now, if we look here at the start bit for reactants, molecules, the molecule bonds are stretching as they have more kinetic energy. So we're giving them a little bit more energy. Remember, this is enthalpy going up here, which is measured in kilojoules per mole. So the molecules are starting to stretch. They have a little bit more kinetic energy. This bit here, when we're giving them more and more and more energy, and eventually what happens is we reach the minimum amount of energy needed for these collisions to happen. And basically, we put a little bit of energy in, and we call this the activation energy. It's always between the reactants and the top of the profile here. This is called the activation energy. So at this point, right at the top, the bonds have sufficient energy to break. So we're breaking the bonds here, and this allows the atoms to kind of break free and collide with other atoms to produce your products. So reactions that have a low activation energy need less energy to break these bonds. Normally, obviously, we heat these things. It's by heat energy, and vice versa as well. So basically, if we get one where we've got a flatter dome here, that's going to be better because we need less energy to actually get the reaction to go and to produce your products. So let's look at the Maxwell-Boltzmann distribution. Okay, so a Maxwell-Boltzmann distribution shows the energy in gas particles. Okay, so these are like funny looking graphs, these things. Okay, so particles in a gas in a sample, they move at different speeds. So they're not all moving at the same speed. So move quickly, some slowly. And they have different amounts of kinetic energy. Remember, that's moving energy. Those of you doing physics will probably recognize that quite well. And if we plot this on a graph, we get what we call a Maxwell-Boltzmann distribution. Okay, so let's have a look at this graph. So you can see here on this axis, we've got the number of molecules, and here we've got kinetic energy. Obviously, it's the kinetic energy of the particles. So the graph starts at 0, 0, because we don't have any particles with no kinetic energy. Okay, so this is down here. So that's the first thing that's really important. And the total area under the graph here, this bit under here, equals the total number of molecules. Okay, so this doesn't change. So we had like 100 molecules in a box, and we looked at the different energies of each molecule, and this is the profile that we get. So the energy underneath, or the area underneath, is the total number of molecules. Okay, this bit where the peak is the most likely energy of a particle in a sample. The bit to the right is the mean energy the particles have. So this is the most likely energy, and this is the mean energy. Don't get these two mixed up. Okay, these could be potential exam questions. So make sure that you know the difference between the two. Mean energy and the most likely energy of a particle in a sample. This bit down here is called the activation energy. It's normally on the right-hand side. Well, it will be on the right-hand side. Most of the particles, as you can see, don't have enough energy to react. Ones beyond this do. So these particles have very little energy, effectively. So these move really slowly down here. So kinetic energy, look, is really low. Ones around about the middle area here, these move with a moderate speed, so they've got a bit more energy, a bit more kinetic energy. They're moving, not quite enough to react though still. And in this zone, like I say, these particles, or particles with energy here, will have enough energy to react because they have energy greater than the activation energy. So it's this bit here where the particles can react. Okay, so let's have a look and see what affects the rate. So temperature affects the rate of reaction. So particles have, on average, more kinetic energy when they're heated, because obviously we're transferring thermal energy into kinetic energy in the particles. A larger proportion of the molecules will have energy greater than the activation energy if we heat them up. And this is the red line. We have a larger area under the curve beyond the activation energy. So the overall area under the curve is the same, because we haven't added any more particles. All we've done is we've heated the particles up. So we get this red line here. Now, if you look, the activation energy, the area beyond the activation energy is now greater. So we've got many more particles with energy greater than the activation energy. So if you look at a few other things as well. So the curve shifts to the right. Okay. The peak is lower because we've got the distribution of energy is now much greater amongst the particles. The area under the curve is the same because we've got the same number of particles, but the area under the curve beyond the activation energy increases. We've got many more particles with energy greater than the activation energy. You've got to make sure you draw your profiles just like this, these key points here. If we look at it when we decrease the temperature then, so when we decrease the temperature, we've got a smaller proportion of the molecules will have energy greater than the activation energy because obviously they've got less kinetic energy. The blue line obviously represents this. So let's look at the points on this one. Again, this time the curve shifts left. You can see the blue one, look, it's really bunched up towards the left. The area under the curve is the same. Again, the peak is higher. Look at the peak here compared to the reference one, which is the white line. Look at the blue one. It's much higher than this one. And the area under the curve beyond the activation energy decreases. You can see here, we've only got this little area now where particles have just enough energy for them to react. Most of the particles don't have enough energy to react. And that makes sense because they've got less energy, less kinetic energy, and it's cooler. Okay, so let's have a look. Why do we get a faster rate of reaction when this temperature is increased? Okay, so we need to look at particles for this one. So the particles move around more at higher temperatures because they've got more energy, collide more often, and this is the reason why reactions happen faster at higher temperatures. More collisions, okay, so they've got a faster rate of reaction. The combination of more collisions and more energetic collisions, because remember they've got more energy, means that a small increase in temperature leads to large increases in rate. So if we have a look at here, this bit is representing the more collisions. This bit is representing more energy. So these two basically means that if we increase the temperature a small amount, we get a much increased disproportionate amount of energy, disproportionate amount increase in the rate of the reaction. Okay, concentration and pressure also affect the rate. So for pressure, if we increase the pressure, we increase the rate of reaction. This is because all the particles are much closer together. We get more frequent collisions, they collide more often, and there's a higher chance of a reaction. It's all about probability and chance. Here's a box showing lower pressure. Look, the particles got a lot more space. At a higher pressure, there's less space for them to move around, so they're more likely to collide into each other. Concentration. So if we increase the concentration, we also increase the rate of reaction. Very similar to pressure, really. The particles are closer together, collide more often, more frequent collisions, and a higher chance of a reaction. You can see here, lower concentration. Look, less red circles here. The reds are less likely to interact with each other. But if you look at this one here, because we've got more red circles, you've got a higher chance of reactions because there's more of them, put it simply. So that's why higher concentration reagents will react that little bit quicker. Okay, catalysts also affect rates. There's loads of things that affect rate here. So a substance that increases the rate of reaction, this is what a catalyst does. What it does is it provides an alternative pathway. You can look at all the underlined words. These are the key terms. And has a lower activation energy. It is chemically unchanged at the end of the reaction. So when we use the catalyst is reformed again. Or if it's a solid catalyst, which we'll look at in a minute, heterogeneous catalyst, they stick to the surface of the catalyst and then are released. We call that adsorb, but we'll look at that later on. So catalysts generally used to speed up a specific reaction. Obviously, we have loads of different types of catalysts we can use, and they're used depending on what the reaction is. So there isn't just one type of catalyst, there's a variety of them. And basically, they make the product faster, and that's pretty good because if we make the product faster, they say in business, time is money, and obviously the longer it takes, the more cost you would have for the business because the customer wants their product quicker. Also, catalysts reduce the activation energy, so they lower the amount of energy required for this reaction to happen. So that saves money in terms of energy. You don't have to heat it up as much. So here's an example of a catalyst. This is a zeolite. It's a solid catalyst. If you look really closely using a microscope, you can see tiny microscopic pores in here. These are called micropores. And this basically increases the surface area of the catalyst and allows reactions to happen much quicker. So you've got more higher chance of collisions on the surface of the catalyst because it's got a large surface area. This is called a zeolite. Okay, so let's have a look at these types of catalysts. So they can be homogeneous or heterogeneous. So heterogeneous catalyst, hetero means different. Okay, so these are in a different phase to the reactants. So and the catalyst is obviously in a different state. So if we have a look here, we've got the Haber process, which is basically the manufacturing of ammonia, nitrogen gas, hydrogen gas, ammonia gas. The catalyst we use is an ion catalyst. Because this is in a different state, because it's a solid, different state to your reactants and products, we call this a heterogeneous catalyst. So it's a solid in a gas reaction. So what this does is basically helps the reaction to speed up, provides an alternative pathway. What we can do with this solid catalyst is increase the surface area of the catalyst, and what this will do is increase the rate of reaction. So turn this iron into a powder, perhaps, and spraying it onto a gauze would increase the surface area. So that's going to be pretty useful when we want a reaction that's speedy. More particles can react with the catalyst at the same time if it's ground down into a powder with a larger surface area. The other type is homogeneous. So these are in the same phase as the reactants. So basically, these are normally in aqueous solutions. So you've got an aqueous catalyst with aqueous reactants. So sulfuric acid is a really, really good example of that. And it's used to make an ester. So that would be a classic example of a homogeneous catalyst. Sulfuric acid is obviously aqueous. The ester is aqueous as well, both in the same state. So homogeneous catalysts, what they do is they form an intermediate. They're a bit different to heterogeneous. So they actually used up initially, form this intermediate by reacting with the chemical that you've got in here. But then crucially, at the end of this reaction, the product that was used is reformed again. So it's actually used up and then reformed. With heterogeneous, it isn't. It's like just the reagents stick to the surface of the catalyst and then desorb and move away from the catalyst. So it's not actually used up. It's just used as like a bit like sellotape, dust on sellotape. So it's like a surface in which a reaction can happen. Whereas this one, the actual catalyst gets involved with the action but is reformed. So How do catalysts affect rate? Well, if we look at the Maxwell-Boltzmann distribution, a catalyst lowers the activation energy. More particles now have enough energy to react. Here it was without a catalyst, here it is with a catalyst. So it shifts the activation energy further left, and so you can see now we've got a larger area beyond the activation energy. That means we've got more particles with enough energy for a successful collision to happen, and that leads to a reaction. And in terms of an energy profile diagram, well, it's a little bit easier, I suppose, with this. Here it is again, reactants and products. Here's the energy profile bit. Remember, the activation energy is the distance between the reactants and the top of the energy profile. This yellow dotted line represents basically the activation energy with no catalyst. But if we put a catalyst in, here's the new one, you can see that now the energy profile is shorter. It's not as tall. That means less energy is needed to get this reaction to go, because the catalyst providing the alternative pathway for this reaction to happen. So the activation energy with a catalyst is obviously smaller compared to with no catalyst. Okay, so why use catalysts? Well, catalysts are used in industry for the following reasons. So they lower the temperature needed, so less money is spent on fuel and less carbon dioxide is produced. They speed up the rate of reaction, provide an alternative pathway, and they also change the properties of a product. Now, this is very specialist, so we can use these Ziegler-Natta catalysts, and what these do is they turn polymers like polyethane into a more dense, or polyethene, sorry, should we say, into a more dense, rigid, and higher melting point plastic. Okay, so that should be polyethene, because obviously it's a polymer. Bit of a typo there. So it's more dense, rigid, and you get a higher melting point. So this would be useful for making maybe plastics that you want to last a bit longer, maybe in a car. So you want them to be a bit more durable than if it wasn't treated. So these are pretty useful. So environmental benefits as well. Lower temperatures and pressures. Pressures means safer. Also less energy required. You don't need to manufacture thick pipes to withstand pressurized gases. So this means you reduce CO2, which is obviously a greenhouse gas, so we don't want much of that going in the atmosphere. And also, catalysts, we have less waste is produced with catalysts, so it means you get better atom economies. You're pushing towards the 100% atom economy. So instead of producing a product via 5 steps, a catalyzed reaction may shorten that to 2 steps. So we're transferring less product from container to container and maximizing our reactants and using as many of the atoms as we can into our product. Catalytic converters, these are found in cars. Basically, these reduce the level of pollution coming out of the exhaust. They're made from rhodium and platinum, so they are very, very expensive metals obviously used in the car, underneath the car in the exhaust. And one of the examples they can use is they convert carbon monoxide, which is obviously poisonous, and nitrogen monoxide, which is also can go into the atmosphere and potentially produce nitric acid, which is acid rain, and it turns it into carbon dioxide, which is not toxic, but obviously still not good, but it's a greenhouse gas, but it's better than carbon monoxide, and nitrogen, which is naturally found in the atmosphere anyway. So the catalyst is removing some of these harmful reactants here, these pollutants, into less harmful pollutants. So there's an example. If you look under a car, you can see obviously there's the exhaust. It's the bit underneath near the front of the car. Those people who are interested, and that's basically the catalytic converter. And it's mounted on a mesh to increase the surface area. Okay, so how can we measure rate in experiments? Okay, so if an experiment produces a precipitate, we can basically time how long it takes for that precipitate to form. So you might have seen this before, like the disappearing cross. Here's the reaction, precipitate's formed. You look down the top of the conical flask and time until the cross disappears. Obviously, we've got issues with this as well because it's difficult to know exactly when the cross has disappeared. It's down to perception. Some people might wait longer to decide that the cross has disappeared. Some people might press the button sooner. So it's really difficult to do that. So use the same person really to try and reduce the errors. The amount of mass lost. So we can stick a conical flask if it produces a gas. Put it on a top pan balance like this. And basically you're measuring how much gas has been released and how much is lost. Reasonably accurate method. If the gas is toxic though, you've got to do this in a fume cupboard. So you've got to take precautions obviously with this. You can also do the volume of gas as well that's produced. This is probably a more common method in which you would use. So basically we're producing a gas and we're measuring how much gas is produced over a specific period of time. So for example, how much gas is produced per minute. Obviously you can change the concentration, you can change the surface area, you can change a few things and measure obviously what effect that is having on the amount of gas produced per minute. So again, we're measuring a rate. So we can obviously use this data and we can plot a graph and we can calculate the rate from a graph. So it can be found from the gradient of a graph. So you can see here that we've got the volume of gas produced in centimeters cubed. So this might be in a gas syringe. And this is obviously over a specific time period. So how much gas is produced per time. So we can use the gradient. Now the gradient is calculated by measuring the change in y over the change in x. So the change in y, remember the y-axis is going up here, x-axis is going along here. So the gradient is basically the rate of reaction. And so the bigger the section of the graph that we use to measure this gradient, the better, because we get more accurate results. So what we can do is try and find the points in the graph where the change in y and x can be worked out easily. So let's look at this example here. So we see we're going along a line and along a line. It's more difficult to do it halfway on some of these lines. So let's work out the changes. So the change here is 6. So we're going from 1 to 7. So the change is 6. And the change going up here is 4. So we're going from maybe 1.5 or half to 4.5. So that difference is 4. So now we've got our differences. Literally, we just put change in y over change in x. So you can see here the difference is 4.6 minus 0.6. We start 4.6 minus your 0.6, so it was 0.6 here. And then we do the same for change in x, which is along the bottom. So that's going to be 7 minus 1. So the gradient is 0.67. Look at the units. This is volume of gas at centimeters cubed per minute. Okay, so that's the units. Make sure you look at the axes to get your units. It's always that divided by that. Okay, so that's relatively straightforward. Sometimes though you don't get straight lines. Okay, so we can work it out by using a curved graph. We've got a curved graph and we measure the tangent of the curve and use that as the gradient to work out the rate. So here's a graph, look. Here's the curve. So this is the mass this time of the reaction vessel. So obviously the mass is dropping because the gas has been lost. That was the second one I showed you. And this is over time. So what we do is you draw a tangent. This is just a diagonal line that meets the curve at a very specific point that we want to measure. And we extend the line right across the graph. So we go all the way along to the y-axis, all the way along to the x-axis. And then we measure that steepness of that line, which is the gradient, at that specific point. So in this example, we are going to work out the rate of reaction at 3 minutes. So we find 3 minutes and we're going to draw a tangent there where it meets this part of the curve. So let's go for it. There it is. Okay, this is your tangent. So we're drawing it right across, diagonal across, and extend it across the full length of the graph. So the gradient, just like before, is the change in y over the change in x. So let's have a look. Okay, so there's our change. So you can see we'll get a nice triangle there. Put your numbers in. So the change here is 0.8. So that's the difference there. And the change here is 4. We stick their numbers in. We do 20.8 minus 20.0. So there it is there. 20.8 minus 20.0. And this one is going to be 4 minus 0 because we've got the change there. And the gradient is 0.2 grams per minute. So officially the gradient will be negative because obviously this one's sloping down, but don't worry too much about that for chemistry. All we're really interested in is the value because that tells us the rate of reaction, how quick this reaction is happening. Look at the units again. This is grams per minute. So that's why the units are there because we measured the mass of the reaction and the time. So this is grams per minute. So relatively straightforward as you can see. And that is the end of this video on reaction rates. As you can see, it's a reasonably good overview. Please subscribe to the channel and support the channel. If you just click on the little circle in the middle there, and you can subscribe and get all the up-to-date videos that are uploaded. And also just a reminder that if you want to purchase these slides, and use them as revision, you can do. Just click on the link in the description box below this video. But that's it now. Bye bye.